Scientists filmed a plant communicating with its neighbor using a sophisticated system of airborne compounds. These imperceptible chemical signals serve plants by repelling herbivores and warning nearby plants about potential threats. While researchers have been aware of these plant defenses since the 1980s, the mechanism behind how plants receive and respond to these signals remained a mystery. To capture this footage, scientists used a pump to transfer compounds emitted by damaged and insect-infested plants onto healthy ones and used a fluorescence microscope to observe the reactions. The experiments involved exposing leaves of various plants to caterpillars and then monitoring the responses of untouched plants to the signals of distress emitted by the damaged ones. Plants communicate with each other as a survival strategy to defend against threats and optimize their growth. They use a variety of chemical signals to transmit information about environmental conditions, such as herbivore attacks or pathogen presence. When a plant is under stress, it releases these signals into the air, and neighboring plants detect them. This communication enables nearby plants to prepare for potential dangers by triggering defensive responses, such as producing chemicals to deter herbivores or strengthening cell walls. Plants can also communicate through underground networks of fungi called mycorrhizae, sharing nutrients and information about soil conditions. These communication mechanisms help plants adapt and thrive in their ever-changing surroundings. Researchers have turned electronic waste into gold using an innovative aerogel sponge made from whey, a byproduct of cheese production. This sustainable technique not only recycles e-waste, but also turns it into nearly pure 22-karat gold nuggets. The process begins by dismantling and dissolving discarded computer motherboards in an acidic solution, then filtering out debris. The aerogel, acting as a gold sponge, is then introduced to absorb the gold ions from the solution. Remarkably, this method allows for the extraction of gold with a high level of purity and efficiency, with a significantly reduced environmental impact compared to traditional methods like activated carbon. The researchers found that to recover 1 gram of gold, only 5.26 grams of the aerogel is needed, making it a third more efficient and reducing the carbon footprint by about 25%. This not only presents a cost-effective way to reclaim gold from e-waste, but also addresses the issue of electronic garbage and waste surplus simultaneously. The team anticipates that this technology could be adapted to extract other valuable metals from e-waste. Around 40 million tons of e-waste is generated globally each year, which is equivalent to discarding 800 laptops every second. E-waste constitutes 70% of toxic waste, yet only 12.5% is recycled. The bulk ends up in landfills or incinerators, releasing hazardous toxins like lead, mercury, and arsenic into the environment, which can severely impact human health, including damage to the nervous system and hindering a child's mental development. Did you know that diamond can be squeezed into something even harder? For decades, diamonds have reigned supreme as the hardest known natural material on Earth. However, diamonds may not hold the title of the hardest material for much longer. Researchers have theorized the existence of a form known as the 8-atom body-centered cubic structure, also known as BC8, which is expected to be up to 30% more resistant to compression than diamonds. Although the BC8 phase has been observed in materials like silicon and germanium, it hasn't been found naturally on Earth in carbon. However, there is strong evidence that it could exist in the high-pressure environments deep inside exoplanets. If scientists manage to synthesize and stabilize the BC8 phase closer to home, it could leave diamonds in the dust when it comes to sheer hardness. Despite previous unsuccessful attempts to create BC8 carbon in a laboratory, the researchers now used supercomputing to understand where these attempts fell short. By running simulations on the Frontier supercomputer, they were able to reproduce the behavior of billions of carbon atoms under extreme pressure and temperature conditions. The results revealed that BC8 carbon can only be formed within a very specific high-pressure and high-temperature range. The researchers are now planning theory-inspired experiments to create BC8 carbon at the National Ignition Facility.